It's not one BB and one laser pulse per day. It's like 5 or 10 times per second, like like that, right? So you're doing it there. And then comes the other aspect. So it's making the targets, delivering them, being able to repeatedly get them to burn. And then we haven't even talked about like how do you then get the fusion energy out, which is mainly because these things are basically micro implosions which are occurring. So this energy is coming out to some medium on the outside that you've got to figure out how to extract the energy out of this thing.
How do you convert that energy to electricity?
So in the end, you have to basically convert it into heat in some way. So most of what fusion makes mostly is like very energetic particles from the fusion reaction. So you have to slow those down in some way and then make heat out of it. So basically the conversion of the kinetic energy of the particles into heating some engineered material that's on the outside of this.
And that's, from a physics perspective, is a somewhat solved problem, but from an engineering still
physics. I can show you all the equations that tell you about how it slows down and converts kinetic energy into heat, and then what that heat means. You can write out like an ideal thermal cycle, like a Carnot cycle. So the physics of that, great. The integrated engineering of this is a whole other thing.
I'll ask you to maybe talk about the difference between inertial and magnetic, but first we'll talk about magnetic. But let me just linger on this breakthrough. It's nice to have exciting things, but. Yeah. In a deep human sense, there's no competition in science and engineering. We're all, like you said, we're broad. First of all, we are humanity altogether. And you talk about this, it's a bunch of countries collaborating. It's really exciting. There's a nuclear fusion community broadly, but then there's also MIT. There's colors and logos, and it's exciting. And you have friends and colleagues here that work extremely hard and done some incredible stuff. Oh, yeah. Is there some sort of how do you feel seeing somebody else get a breakthrough and using a different technology? Is that exciting? Does the competitive fire get
all of the above? I mean,
the ignition.
I have to wave the flag a little bit. So MIT was a central player in this accomplishment. Interesting, I would say it showed some of our two best traits. So one of them was that how do you know that this happened? This measurement, right? So one of the ways to do this is, if I told you, is that in the DT fusion, what it actually, the product that comes out is helium. Mm-hmm. We call it alpha, but it's helium, and a free neutron, right? So the neutron contains 80% of the energy released by the fusion reaction, and it also, because it lacks a charge, it basically tends to just escape and go flying out. So this is what we would use eventually for. That's mostly what fusion energy would be. But so what my scientific colleagues at the Plasma Science and Fusion Center built were extraordinary measurement tools of being able to see the exact details of not only the number of neutrons that were coming out, but actually what energy that they're at. And by looking at that configuration, it reveals enormous. I'm not gonna scoop them because they need to publish the paper, but it reveals enormous amounts of scientific information about what's happening in that process that I just described. So exciting. I mean, and I have colleagues there that have worked like for 30 years on this for that moment. Of course you're excited for them. I mean, and it's one of those, like, there is nothing, it's hard to describe to people who it's like almost addicting to be a scientist when you get to be at the forefront of research of anything. Like when you see like an actual discovery of some kind and you're looking at it, particularly when you're the person who did it, right? And you go, no human being has ever seen this or understood this. It's pretty thrilling, right? So even in proxy, it's incredibly thrilling to see this. It's not, I don't know, it's rivalry or jealousy. It's like, I can tell you already, fusion is really hard. So anything that keeps pushing the needle forward is a good thing. But we also have to be realistic about what it means, to making a fusion energy system. Yeah. That's
and then, but that's the fun. I mean, these are still the early steps. Maybe you can say the early leaps. So let's talk about the magnetic confinement. Yeah. How does magnetic confinement work? What's the tokamak? How does it all work?
So go back to that. So why inertial confinement works on the same principle that a star works. So like, what is the confinement mechanism in the star? is gravity, because its own inertia of the something the size of the sun basically pushes literally a force by gravity against the center. So the center is very, very hot, 20 million degrees, and literally outside the sun, it's essentially zero because it's vacuum of space. How the hell does that do that? It does that and it's out of thermal. Like, why doesn't it just leak all of its heat? It doesn't leak its heat because it all is held together by the fact that it can't escape because of its own gravity. So this is why the fusion happens in the center of the star. Like, we think of the surface of the sun as being hot. That's the coldest part of the star. So of our own sun, this is about 5,500 degrees. A beautiful symmetry, by the way. It's like, so how do we know all this? Because we can't, of course, see directly into the interior of the sun. By knowing the volume and the temperature of the surface of the sun, you know exactly how much power it's putting out. And by this, you know that this is coming from fusion reactions occurring at exactly the same rate in the middle of the sun.
Is it possible, as a small tangent, to build an inertial confinement system like the sun? Is it possible to create a sun?
It is, of course, possible to make a sun, otherwise we wouldn't have stars. But it is not impossible on Earth, because for the simple reason that it takes the gravitational force is extremely weak, and so it takes something like the size of a star to make fusion occur in the center.
Well, I didn't mean on Earth. I mean, if you had to build like a second sun, how'd you do it?
You can't. There's not enough hydrogen around. Yeah.
So the limiting factor is just the hydrogen.
Yeah, I mean the forces and energy that it takes to assemble that is just mind-boggling.
All right.
So we wouldn't do that.
To be continued.
Yeah, to be continued. So what are we doing it with? So in the one that I just described, it's like you say, so you have to replace this with some force which is better than that. And so what I mean by that is it's stronger than that. So what I talked about, the laser fusion, this is coming from the force, which is enormous compared to gravity, like from the rocket action of pushing it together. So in magnetic confinement, we use another force of nature, which is the electromagnetic force. And it's orders and orders of magnitude stronger than the gravitational force. And the key force that matters here is that if you have a charged particle, that namely it's a particle that has an net electric charge, and it's in the proximity of a magnetic field, then there is a force which is exerted on that particle. So it's called the Lorentz force, for those who are keeping track. So that is the force that we use to replace physical containment. So this, again, confused. So how do you hold something at 100 million degrees? It's impossible in a physical container. This is not like, it's not this plastic bottle holding in this liquid or a gas chamber. What you're doing is you're immersing the fuel in a magnetic field that it basically